Yes, very good morning. So in our previous class, we discussed about solar energy collectors. Okay, so which is deals with the second module. So in today's class, we are going to discuss about a different types of solar energy storage. Okay, so in previous class we discussed about collectors, and in today's class we are going to discuss about storage, a solar energy storage system. So the solar energy, it's a time dependent. We already know that it's a time dependent and intermediate energy resource. It's a time dependent as well as intermediate energy resource. It depends on the time and it is not continuously available. So in general, the energy needs for demands of a very wide variety of applications are also a time dependent. It is also a time dependent, but it is an entirely different manner from the solar energy supply. And there is a mark needed of energy storage and other product with a solar process. We need it. And if the solar energy is meet the energy needs, if our solar energy capability to meet our energy requirements, then we have to use so many processes to store the energy. And this problem is especially severe for a solar energy when it is used for a beating in winter. So the problems will occur, it is in the winter, okay, because of its a low availability during this period. So especially the solar energy problem is arises where in the winter and rainy seasons, because in the rainy season and winter the availability of the sun or the solar radiations or the solar insulations are very less. So the problems will occur in the winter and rainy seasons. So to overcome this, we have to go with a solar energy storage system. The need of energy storage of some kind is almost immediate evident for a solar electric system. Means a solar energy storage system which is an immediate evident for solar electric systems. And optimally designed solar electric systems will collect the solar energy and convert when the radiations is available during the daytime. The radiations are available only in the daytime, not in the night time. So that solar electro systems will collect the radiations and convert and storage. Okay, so unfortunately the time when the solar energy is most available will rarely coincides exactly with the demand for electric energy. So so the solar energy is available in the daytime, that too in the noon time it is more availability when compared to the morning and evening time, but the electric need is very less in that time. So in the noon we need a very less electrical supply or electricity when compared to the morning and evening time. Evening and morning time we need a more electric energy rather than the noon time. But the solar availability, the solar rays or solar insulation availability is more in the daytime, that too in the noon time, but less in morning and evening time. So this is a reverse process. Okay, so thus both tends to peak during the daylight hours. So there is a problem of clouds and photovoltaic plants, and cloud cover with several days may result in a subsequently a lowered electric output compared with a high radiation or cloud free day. High radiation day, it is also called as a cloud free day. Okay, so obviously during such a energy previously stored, means if you stored energy where the energy is very high, where the peak availability of the radiations, we can collect and we can store the energy. So the previously stored energy during a high radiation time could be used for provides a continuous supply where the radiation is very less or where the energy is required. So this is a one advantage of storage of energy, means in sometimes the solar radiations are continuously available. So at that time the demand is also very less. Okay, so demand is less, the availability is more. So what we'll do, we have to collect as much as possible radiations and stored. Okay. And next, when the radiations is no radiations, where the energy supply is increases or demand is increases, then we have to supply the solar stored energy for utilization purpose. Okay, so that's why we need a solar storage system. Storage of solar systems in a solar system may depends. The first is it permit a solar energy to capture. This solar system, the solar collectors already we discussed, but the solar storage, once we collect and convert, then we have to store that energy. Okay, so this is what the solar energy storage. So this storage will permit solar energy to capture. First it will capture when the insolation means when the radiation is highest, and then later used when the need is greatest. Okay, the highest radiation which is not equal to the need is greatest. When the time of highest radiation, the need is less, but when the time of highest need, the radiation is less. Okay, so first it will permit to capture the radiations, and it transfers that solar energy into a different forms, maybe electric forms or maybe thermal input. Means first it will capture and it will convert either electrical or thermal. Thermal means it's in the form of heat, so it will convert. That is the first step, this solar system. Then make a possible delivery electric load power demands during a time when radiation is very low. Means it will supply the radiations, it will supply the energy where the radiations is low. Maybe electric already captured and stored in the form of electrical or heating energy. The classification of storage we will discuss in the later. Okay, so normal or a non-existence. A storage also makes it possible to deliver a short peak of power for exceeding the rated power capacity of plants. Okay, when the plant capacity is so much, like 20 kilowatt, so it will collect the solar energy and stores. When the need is highest, when the need is greatest, then it will continuously supply the energy. Okay, this can be possible. And the next is be located closer to the load. Be located closer to the load means the storage system, we can locate the storage system where the need is there, where the load is needed. We can locate the storage system near to the load, thereby minimizing the need for a costly transmission. For example, okay, take an example of hydropower plants. Example of hydropower plant. What happens hydropower plant? So in the hydropower plant, the generation of electricity is near the where the dam is there, where the storage of water is there. Okay, it is somewhere in the forest, it is somewhere in the hilly regions. Okay, but the energy requirement is in the urban or villages. It is so far distance from the requirement and the availability, so it needs a large transmission system. So where the large transmission system, there is a larger in the losses. Okay, so here we can reduce that loss. Means we can collect and we can store the energy where the load is required. So we can avoid or we can minimize, not completely eliminate, but we can minimize the loss, transmission loss and distribution facility. We can reduce this. And next, improve the reliability of the solar thermal as well as solar electrical systems. We can reliability means we can trust on the process. So here if there is no storage means we cannot reliable on the solar energy. If there is no storage, if instantaneous generation and instantaneous use means we cannot trust or we cannot reliable, because the solar energy completely it is depends on the daytime, nighttime. It is peak in some hours and it is low in the some hours. It is completely depends on the orientation, latitudes, everything. It is intermediate. Okay, so that we cannot reliable like conventional source of energy is like coal, petroleum. But here, if you reliable, when we use a storage system, if we use or if we include the storage system, we can easily reliable, because storage systems will store the energy, the excess generation of energy is stored, and it will release where the need is there. That's why we can easily trust or reliable. So next is permits a match between the solar energy input and the load demands. If you use storage system, it will match the requirement as well as generating the energy and storing and supplying. It will match that equation. Okay, so these are the some advantages why you have to go with the storage of electric energy. Clear? The optimum capacity of an energy stored depends on general of factors. Means optimum storage of energy, optimum storage. So far we discussed what is the advantages, or why we have to go with the solar energy storage. Okay, so why we have to go, that what we discussed, some few points. Similarly, similar kind of we discussed the optimum capacity of energy storage. That system depends on some of the factors. The storage is also depends on some of the factors. The first factor is the expected time dependency of solar radiation availability. The storage is more where the availability is more. If the availability is less, the storage is also less. So the storage is direct, the direct factor is the availability of the radiation. Clear? That is the first factor which decides the solar energy storage. A second, the nature of load to be expected on process. A nature of load means we need a heavy load, we need a low, we need a medium load. So that need of load is also decides the storage factor. If heavy load required, we have to go with a heavy storage system. If medium load, so medium storage. If the low load, so low storage. So load is also direct factor for the storage. The degree of reliability need for process that I told, the reliability means where we can trust that. Okay, so we can blindly trust that solar energy, and we can go with our operations, like if industry purpose. Okay, so if industry or if there any other than the household purpose, means they need a continuous supply of energy, so they are blindly trusting, means it is because of the storage. Okay, next, the manner in which auxiliary energy supplied, means it need a auxiliary supply systems. Okay, the continuous auxiliary supply systems. Then the size of the solar thermal power systems are a solar electric generators, means the solar electric generators which converts one form to another form. So that also decides the storage factor. Next, the cost per kilowatt of the stored energy. The cost, it's the ultimate. The cost is also decides. If the storage systems become heavy or costlier, then the whatever the energy we are supplying, it is also become costlier. So the cost per kilowatt of the storage system also n factor. It should be as minimum, means economical. Next, the permissible capacity cost located to the storage, and environmental and safety considerations. That is also an important factor. That is environmental and safety consideration, means that solar energy storage system should be safer, because storage means we are storing the energy. There is chances of explosion, there is chances of blast. Okay, so safety is very important. And also environmental means we are storing one energy, means it may chances to eliminate some other harmful radiations. Okay, that is what the environmental, it may harm to the environment. So it is also another factor, the environmental and safety consideration. And ultimately these all things will become the very economical one. Then only the economical analysis, then only we can use. If it is costly, so no one will use. Okay, so these are the factors which decides the energy storage system. Okay, the energy storage may be in the form of, I told, it may be in the form of so many types, maybe heat energy, maybe electrical, or maybe chemical, or mechanical, whatever it may be, a different form. But this after storage, okay, after storage, it should be reversible. It should be reversible. We are storing energy means we are collecting energy from the sun. We are collecting the energy from sun in the form of rays or radiations. Then we'll convert that rays into or radiation into heat, electric or mechanical. Okay. Then we are going to store, or it may be chemical. We are going to store. And wherever we required, it should be reversible process. Means chemical to again electrical, mechanical to again electrical, heat to again electrical, like this. Ultimately what we want a useful form. Okay, it may be in the form of electricity or maybe in the form of heat energy for cooking purpose, whatever it may be. Okay, so whatever the stored energy, it should be reversible form, because the stored energy we cannot directly use. It should be convert and we can use. Clear? So this factor or this should be satisfied by this storage system. Clear? So come to the broad classification of this solar energy, a broad classification of solar energy. So this is a classification chart. Okay, so the solar energy storage technology can be categorized. Okay, this is what the solar energy, it can be characterized, or it can be classified 4 important subgroups. Means the storage system is different for different processes. If I stored in the mechanical energy, if I stored in the electrical energy, means the storage, the conversion. Okay, after conversion, how we are going to store the energy, whether I am going to store it in the form of mechanical, whether I am going to store it in the form of electrical, whether I am going to store it in the form of thermal or chemical. So these are the 4 important types where we can store the energy. Okay, so first it is in the form of mechanical. If I stored that available energy in the form of mechanical, we know that what is meant by mechanical. Mechanical means it may be in the movement. So whatever the movement or rotations or linear motions or rotation motions, it is called a mechanical storage. Okay, you just observe your watch. In some of the watches earlier, we won't use any shells for that watches. Only we are giving a rotations. A small one thread is there. We are going to rotate. Okay, if you keep on rotating means it will store the energy. It will store it in the form of mechanical energy. And once it reaches the maximum, okay, we'll stop rotation and slowly it will reverts. Slowly it will rotate back and provides the necessary energy. You just observe in the watches or in the clock. In the clock also. Okay, so earlier the clock is the clock rotating with the help of mechanical energy, not in the form of electrical or shells. It is in the form of mechanical, means we are rotating some coils. By rotating the coils, we are providing the energy, store the energy, potential energy, and the potential energy slowly converted into kinetic energy and provide the supply. So that is what the form of mechanical storage. Okay, so this mechanical storage of energy, the first one is mechanical storage of energy. It is in the form of potential energy and kinetic energy. So mechanical energy either in the potential and kinetic. So potential means stored energy. Okay, kinetic means with respect to the motion, with respect to the movement. So again, this potential energy can classified a compressed air and pumped hydraulics. Okay, so pumped hydraulics or a compressed air. This is a classification of potential energy. If you use potential energy, if you use kinetic energy, of course, flywheels. You people already know that what is meant by flywheels. So flywheels are generally in IC engines you studied. The flywheels is used to store the energy and it will release the energy where it requires. The flywheel act like a battery, just like a battery. It will store the energy where excess energy is generated and it will supply the energy where it requires. In the IC engines, okay, there are 4 strokes. First one is suction, next compression, working, and last one is exhaust. Okay, there are 4 strokes. Only in the 4 strokes, the working stroke only it will generate the energy, and rest of the 3 strokes will run with the help of this flywheel. The flywheel runs the rest of the suction stroke, compression stroke, and exhaust stroke. Okay, so in the IC engine you already studied in the basic mechanical engineering. Okay, so that is the function of flywheel. So flywheel, it is in the kinetic storage of energy. Flywheel stores the energy. It's a one thing. If you go with the electrical type of storage, that is what electrostatic energy storage or magnetic current energy storage. Electrostatic energy storage or magnetic current storage. So electrostatic means capacitors and super capacitors. Capacitors and super capacitors will store the energy, okay, in electrostatics. And magnetic current means it is an superconducting magnetic energy storage with the help of magnetic, okay, north and south poles, okay, magnetic supply, superconducting magnetic energy can store. So this is another type. And thermal storage, a thermal storage, that is what a low temperature energy storage and high temperature. Thermal means high temperature or low temperature. Thermal means related to the heat and temperature, only heat and temperature. Okay, there is no kinetic, there is no mechanical, there is no electrons. Okay, here only a temperature and heat. So here if it is low means aquifers are cryogenic. Okay, that is what low energy storage. But high energy storage means sensible heat and latent heat. There are sub classifications. And the last one is chemical energy storage. So chemical energy storage means it is a chemicals, yes, okay, electrochemicals and thermochemicals energy storage, chemical energy storage, electrochemical energy storage, and thermoelectrical energy storage. Again, there are sub classifications. And if it is chemical energy storage means with the help of chemical reactions we are going to store the energy, that is battery. In most of the batteries the energy is stored in the form of chemical reactions. Okay, and if it is electrochemical energy, if it is electrochemical means it is a fuel cells. We are using fuel cells. Fuel cells is another type of energy storage systems. And thermochemical energy means it is an solar hydrogen or solar metals and solar ammonia and solar methane. So these are the different types of substances or materials we are used to store the energies. Okay, and another classification is there, electromagnetic energy storage. With the help of electromagnetic process it will store the energy. So these are the broad classification of energy storage system. For your syllabus we are going to discuss, there are two important type of energy system, that is what in the thermal sensible heat storage and latent heat storage. Only two things we are going to study as a storage system. Okay. Yes, before going to sensible heat storage and latent heat storage, we should know what is that. Okay, so these will comes in the thermal storage. I told these two comes in the thermal storage. So there is a mechanical storage, there is a electrical storage, thermal storage, and chemical storage. So in that we are briefly discuss only a thermal storage. In the thermal storage there are two important, one is sensible heat and latent heat. So thermal storage means energy can be stored by heating and melting or evaporation of materials. Heating, melting, and evaporation of materials or any substance, materials or substance, and energy become available. That energy become available a heat when the process is reversed. If the process is reversed, we will get back heat. Okay, if the process will takes place, it will store the heat. If the process will reverse, it will give back the heat. That is what the thermal storage. Okay, so in that thermal storage I told a sensible heat as well as a latent heat. So what is that sensible heat? So which one we call it as a sensible heat? You just observe the graph. Okay, so the graph is a temperature versus stored heat or heat. Okay, and here in the another figure you just observe a sensible heat versus latent heat. First we'll define what is meant by latent heat. Okay, the latent heat, it is the amount of energy, that is either observed or released. Either observed, it will absorb the energy, or it will release the energy during a phase changes at a constant temperature. at a constant temperature. Phase changes means, let us take an example of water. So water has a three phases. One is solid, liquid, gaseous. So phase changes solid to liquid, liquid to gaseous. That is what the phase changes. So this phase changes means gaseous to liquid also phase changes, liquid to solid also phase changes. Here by absorbing the heat, it will change gaseous to solid to liquid, absorbing the heat. If you heat the ice, so ice is the best example. So if you heat the ice, what happens? Ice will absorb the heat and it will start melting. Absorb the heat, start melting, become a water. It will change the phase. If you release the heat, the same. If you reverse the process, if you release the heat means by condensing. That is what in the fridge. Fridge, what happens? By releasing the heat, by rejecting the heat, the water will become an ice. The water will become an ice by releasing the heat. This is a process, either absorbing or releasing. Clear? It will change the phase. So this is what latent heat. Okay. So latent heat, it is an internal energy system, which is with respect to the internal energy system, and all these will take place in a constant temperature. The temperature won't changes. Only change of phase will take place. Temperature is constant. That is what latent heat. Then what about the sensible heat? Sensible heat is the energy required to change the temperature of a substance without phase changes. Means it won't change the phase. If it is in the liquid, it is liquid, but only change the temperature. If it is solid, only solid, it will rise the temperature. If it is gaseous, only gaseous, it will rise the temperature. That is what sensible heat. So in the graph you can see here 0 degree. If you slowly heat the water, okay, means adding the heat, the temperature will slowly rises. Okay, temperature rises and heat increases. But it is in the water. It is in a water only. Clear? Liquid phase. And next, water at an 100 degree. If it is 100 degrees centigrade, what happens? It will start boiling. It will start changing the phase. So this phase is called as a latent heat. Here it is a constant temperature, but heat will increases and change the phase from liquid to gaseous. And once it reaches the saturation temperature, means all the liquid will convert it into gaseous. Then again, if you heat the water, liquid, it won't change the phase because already it is become an steam. It is already become an steam, and this is only raises the steam temperature. It won't change the phase because already it changed gaseous. Further, there is no change of phase. Gaseous is the ultimate. Okay, so it's a sensible heat means the temperature is constant. Temperature changes but no phase changes. But latent phase changes, temperature is constant. For example, in the second figure, you just observe. Okay, water is there. So in the water, sensible, if you keep on 15 degree water temperature and up to 100 degree, there is a sensible heat. Means the water is same water, but only raises the temperature of the water. But in the second figure, it is in the 100 degree centigrade, and further adding the heat, it won't rise the temperature, but it will change the phase from liquid to gaseous. This is what the gaseous, but temperature is same. This is called as a latent heat. This is called as a sensible heat. And these two concepts, okay, by using these two concepts, we are going to store the energy. By sensible heat, by latent heat, also we can store the energy in the form of heat, because in the both sensible heat, latent heat, whatever it may be, the heat is there. Okay, so heat is always there. Q is the heat. But latent heat, temperature is constant. But sensible, temperature is rises. But temperature different. But heat always there. Okay. So by using this concept, we are going to store the energy. Yes. First, we are going with a sensible heat storage. Okay. The first type of heat storage is sensible heat storage. Sensible heat storage, it involves the material or substance. It involves the material or substance that undergo no change in the phase. I told sensible heat means no change in the phase, only change in the temperature, only keep on changing the temperature. no change in the phase over a temperature, a domain or encounter, means temperature changes may change in the storage process. The sensible heat storage means it is a storage of heat energy which involves the substance or material that undergo no change in the phase, only change in the temperature in the process of storage. The basic equation, whatever the basic equation we are using, this is that shown in the slide. Okay, so this is the basic equation, general equation we are using. Dou Q, Q is the heat stored. Okay, dou Q means a small amount of Q, which is equal to M integration of T1 to T2. There is a change in the temperature T1 to T2, Cp capital T into dt, means integration. If we apply integration, okay, we'll get the a final equation, that is what? Qs, heat of the system, sensible heat of the system, which is equal to M into Cp into T1 minus T2. That is the ultimate equation, where Qs or dou Q is the energy stored, energy of the system, energy or a heat energy of the system, which having an unit joules. Okay, m small m is the mass of the object or a substance, mass of the object or a substance. It is in terms of kg. And Cp, so Cp is the specific heat capacity of the system or a substance. Specific heat means how much energy is absorbed or how much energy is given. That is a specific heat capacity of the system. Joules kg, joules per kg Kelvin, joules per kg Kelvin means per kg how much it is absorbed, per kg how much energy is released. That is the capacity, that is in terms of Cp. And dt, which is meant by change in the referencer, that is what? Change in the temperature means, difference in the temperature means T1 minus T2. T1 is the lower temperature, T2 is the higher, T2 is the higher lower temperature, T1 is the higher temperature. Like this, there is a change in the temperature. T1 minus T2 may be 10 degree, 20 degree, 30 degree, 40 degree, like this. So that will directly relate to the how much energy is stored. Okay, if more the change in the temperature, more the energy. If more the mass of the object, more the energy, means it directly related. If more energy, more heat means more mass required, more change in the temperature required, more specific heat required. If more specific heat, more mass, more change in the temperature will result in a more energy storage. Clear? The ability of a store thermal energy is given. If it is in terms of volume, then we can Qs divided by means energy per system divided by volume, which is equal to a rho Cp delta T, means mass we can, so mass we can written as rho by V, means density by volume. Okay, if you want density, so density is equal to volume into mass. So like this we can classify. So here if I don't want mass, means in terms of volume, yes, Qs by volume, which is equal to rho density of a storage media or substance, which is equal to Cp by delta T. Clear? And this the temperature ranges over which a system can be operated is limited. It is limited at a lower extreme by requirements, and the upper limit of the process of the various pressure, okay, vapor pressures and liquids, ability to store this have in terms of volume. And the ability of a storage heat depends on some of the factors, like I explained, density, Cp and volume, as well as change in the temperature. These will decides. Okay, and materials which is used for, so which type of materials we can use, means the substance we can use for this sensible storage is, we can use a water first, and very economical one is water. Then we can go with a rock, then we can go with a gravel or a crushed stone we can use. Okay, iron shots we can use, iron ores we can use, concrete we can use, refractory materials like MgO, Al2O3, aluminum oxides, silicon oxides, magnesium oxides we can use. So these are the refractory materials. So these substances we can use for this sensible heat storage system. Okay, and this is a come to the different categories in the sensible storage systems. Okay, we discussed sensible heat storage. So sensible heat storage means heat is stored in the form of no change in the phase, but only change in the temperature. Okay, so in that the best two examples are water storage and packed bed exchange storage. There are two examples. One is water storage and other one is packed bed exchange storage. The first one is water storage. So in the figure, in the slide, you just observe it is the water storage system. So the most common heat transfer fluid of an solar system is water. So it's a very cheapest and a very economical and easily available. And it is easy way to store the thermal energy as by storing the water directly. Storing water in the directly and well insulated tank. It is stored in the well insulated tank. The optimum tank size for the flat plate collector systems is as usually about 70 kg per meter square, means 2 gallons per feet square. Okay, so water has the following characteristics. Why we have to go with the water? It's have some advantages, like water is an inexpensive. It's a I told it's a very economical and easily available. So water is an inexpensive and ready to available. So water is a ready to available and useful material for storage sensible heat. There is a one factor. Second factor, it has a high thermal energy capacity. When compared to the others, it have a high thermal capacity, storage capacity, high thermal storage capacity. And energy added and removal from this type of storage is done a medium itself. Means we can store the energy, okay, by giving the energy, and by reversing the process we can release the energy. By itself only we can reverse the process, stores and release the energy. And pumping cost of water is also very less. Okay, so these are the advantages why we have to go with this water storage systems. Here there is a typical water storage systems. Here there are two types. One is an with a pumping system, and without pumping system also we can use. For this, best example is your water heaters. So whatever the water heaters used for household purpose or industrial purpose is the best example, which is comes under the sensible heat storage systems. So here so this is what the collectors. Okay, so here the solar collectors, these are the two collectors. Okay, so where it will collect the solar energy or solar radiations from the sun, and we already discussed what is meant by collectors. Okay, it will collect and it will convert solar energy to heat energy, that is Q. Okay, and heated this energy or media which is from this, okay, a flow direction, and check wall, it will maintain the antifreeze. Okay, and there is a check walls as well as antifreeze box. These two are installed, and check wall will supply a constant supply, so constant flow rate. Okay, and this antifreeze box will avoids the freezing of this substance. Then through this it will come to the storage tank. Okay, here it will connect with the coils. Okay, hot water outlet here, and there are inlet water, and through this a coil, that substance, heated substance from the collector will flowing. Okay, like this it will flowing, again it will back into the collectors. Okay, from the collectors through this exchanger, it will through the exchanger, again from the exchanger it will connect back to the collector. It is a closed circuit. Clear? So there is no loss in the substance or mass. Again in the exchanger, these coils are surrounded by water. So water input. Okay, so here a cold water as a input, and another side there is a hot water. So this cold water, while flowing, it will circulate around the coils. Okay, so it will circulate along the coils, and this along in the coil there is an hot liquid flowing, and that hot liquid will exchange the heat from hot liquid to that water, and that water will absorb the energy, and it is become a hot water as a output. Clear? And here pump we used, so that pump is used to circulate the substance from the collector to the exchanger to the collector. For that purpose we are using the pump. Okay, and entire this exchanger is insulated with some materials. okay, just to avoid the loss. This is the one typical arrangement. And another typical arrangement is without pumping systems, directly solar collectors and a one-way check valve, only one way solar collector from this. Okay, there is an heat exchanger, auxiliary heaters, and here hot water and cold water is connected, and along that it will circulates and it will exchange the heat. Okay, so these are the typical two systems where it will collect, okay, then it will convert, then transfer, and it will stored in the system. So this is a typical water storage system. So second one is a packed bed exchanger storage. A packed bed exchanger storage. This is. So in the packed bed, it is also a sensible heat storage with a air as a energy transport mechanism. Here as a transport medium, it is also sensible, and here as a transport media. Here we can use rock, a gravel, crushed stone, and a. So we use a rock, okay, gravel, or air as a transport media. Here we are not using an water, air as a transport media, and that consists of a rock, gravel, okay, crushed stone. So in the basin, okay, this is what the typical arrangement. Here you can just observe it is a typical arrangement. Okay, so this is a basin which contains a rock, okay, gravel, and a crushed stone. Here also same thing. Okay, and here so this will it's a very cheap when compared to the water because air is freely available, and in the thermal capacity, however, it's only about an half of that water, and the basin volume within 3 times volume of the water tank, and the heat over the same temperature intervals. Water is a superior because of the low thermal material cost, and water volume required per unit storage energy. Means here need a large volume when compared to the water. Okay, and following advantages when compared to the water is rock is more easily contain the water. Okay, and rock act as an own heat exchanger. It will conduct the heat very easily, which reduce the total system cost, and it can be easily used for thermal storage and a high temperature and much higher than the 100 degrees centigrade. And storage at a high temperature, the water cannot be used for a liquid, but here we can easily used. Okay, and the heat transfer coefficient between the air and the solid is very high when compared to the water heat transfer coefficient, and the cost of storage material is low because we are using a rock and air. It's a very cheaper, and the conductivity of the bed is low when compared to the water. Okay, so this is what the typical bevel bed exchanger. This is the one, a typical bevel water exchanger. Okay, so here the collector, this is the collector where it will collect and transfers heat to the air, and that hotted air it will pass us through the packed bed heat exchanger. This is a packed bed heat exchanger, and this is our two outlets. One is air flow and air flow. Here air is connect with the collectors, and here is connect with the other systems, and in between that there is an intermediate layer that is called packed bed heat exchanger. So this packed bed heat exchanger, okay, one side that hot air flowing and another side cold air is flowing, and it will, this packed bed will transfer the heat from one side to another side. It will distribute the heat from one side to another side. Okay, so this is how it will transfer, and another that hot air we can use for other any useful purpose like generating the electricity, and here in the another side the same water air is used for recirculate the collection of that radiations from the collectors. Okay, here it is a closed one and here it is a closed one. Okay, so between that there is an intermediate layer called packed bed heat exchanger. The packed bed is with an rock, gravel and crushed stone. Clear? So here we can just observe heated fluid with the collectors. Here we connect with collectors. Okay, here we connected the collectors. Here it is a collector, and it will heated fluid, and it will flowing along the packed bed, and it become a cold fluid, and again back to the collectors. and here there is an heat exchange from the bed, that the coil to the bed. Okay, and the bed again with an other substance surrounded by another substance, where it will absorb the heat and it will store and it will convert electric energy or chemical energy, whatever it may be. So this is a typical packed bed heat exchanger. Okay. Okay. So next is last one is latent heat storage. So latent heat storage, I told, it is an transfer of temperature. Temperature is constant, but only it will change the phase, but temperature is constant. That type system is called latent heat storage. In the latent heat storage, the heat stored materials when melts and extract from the material when it is freeze. And material that undergo change in the phase in the suitable temperature range may be useful. Means temperature is either constant or it's a suitable change in the temperature. And it is following some of the criteria to be satisfied. Means the phase changes must be accomplished by high. Yes, sorry for the inconvenience. The next thermal storage, the another type of storage is latent heat storage. The latent heat storage, we already know that it is a type of storage where the temperature changes, but there is no phase changes. Okay, here we use the material or substance when it melts and extract from the material when it freezes. The material will undergo a change in the phase in a suitable temperature ranges may be useful for this type of storage. And some of the characteristics I told, that is what we are going to discuss. The first characteristics or first criteria should satisfy this type of storage is the phase changes. Okay, the phase changes must be accomplished by high latent heat effect. High latent heat effect means it will absorb the more heat. More heat absorb means high latent heat effect. This will take place in a high latent heat. Second, the phase changes must be reversible. Means the phase change, liquid to gaseous, gaseous to liquid, there is a phase changes. It should be reversible over a very large number of cycles. Okay, the phase changes must be reversible over a large number of cycles without degradation. Means the substance we are using for n number of cycles, we are using the same fluid. So that if n number means n number of change of phase, if n number of changes of phase means it should avoid the same property, it won't degrade. If you degrade means it will change the property and it will reduces the effectiveness or efficiency. Next property, the phase changes must occurs with a limited supercooling. Means it should be a very low supercooling. It is a supercooling or superheating should be very low. It is very low, then only it is efficiency is high. If the more supercooling or more superheating means it will change its efficiency, it reduces its efficiency. The must available to contain a material transfer heat it and out it. It will absorb the heat and it will release the heat. That heat absorb and releasing should be as much as equal. Okay, and the cost of materials and the containers must be reasonable. That is most important. Cost and the whatever the the necessary tools we are using, that should be a very nominal one. The phase changes must occurs close to it and actual melting temperature. The phase changes must occurs close to its actual melting temperature. Okay, means the melting temperature and the change of phase must be actual. It means be same. The material must be available large quantity. So if the material available in the large quantity, then it is become an economical one. If it is a rarely available, then it is become a costlier one. Then the preparation of the this phase changes during the material must be relatively simple. Whatever the process we are using, the phase changes should be very simple one. In the simple process, it will change liquid to gaseous, gaseous to liquid. And the material must be harmless. They are non-toxic, they are non-flammable, non-combustible, non-corrosive. So these are the properties, best properties of the substance. That substance, whatever the substance we are using for the system, should be non-toxic. It should not having any toxic content, and it is not inflammable. If it is inflammable, it will start the combustion process and it will destroy entire thing. So it is inflammable, it is a non-combustible and non-corrosive. It also non-corrosive because this substance will flowing through the coils, metallic coils. If it is corrosive, it will destroy the metallic tubes, so that it should be non-corrosive. A small volume change during the phase changes means a small volume changes during the phase changes means it will absorb more heat and it will change very less. That is the best property of a substance. And the material should be have a high thermal conductivity. That is the most important thing. The material should have a high thermal conductivity. Then only it will absorb a much thermal energy and it is become more effective. If it is more absorb the energy, it is become more effectiveness, so that more thermal energy will be stored. So these are the some properties or criteria should be satisfied for latent heat storage system, not for the sensible, only for the latent heat storage system. Okay, if this figure you just observe, and for this we can use some of the materials, like we can change a phase easily. That is what we use. Several materials are a Glauber salt. We can call it as a Glauber salt, that is Na2SO4, Na2SO4 or 10H2O. Na2SO4 or 10H2O, it is called Glauber salt. Okay, it is a one material. Or we can use water, or we can use FeNO32 or 6H2O or any other inorganic or organic materials we can use as a substance for this type of systems. Generally they are using Glauber salt. That is what Glauber salt means, Na2SO4 comma 10H2O, 10 unit of H2O. So if you go with the equation Na2SO4 10H2O plus energy, which give rise to Na2SO4 plus 10H2O, which releases the energy. Clear? So take place the equation for the reaction, it will energy is stored, and by reversing that equation it will energy released. Clear? So a typical storage system you just observed in the slide. These are the collectors. Collect the solar energy, convert into heat, and this is a high into salt heat exchanger here, and it is connected with the coils. Okay, so coils continuously having the substance. I told the substances are water or Glauber salts, or it may be used Fa2NO3, 6H2O. There are different materials, or else we can use a organic compound substances also we can use, like paraffin or fatty acids also we can use. So these are the substances we are used, and they are continuously flowing along this coil which connect the collectors. And here there is an heat exchanger. It is a oil to salt heat exchanger. Inside the heat exchanger there is an heat exchange. Here in the collector it is absorbed by the substance, and in the heat exchanger it will give the heat to the another substance. Okay, and here that heat exchanger there is a substance which are hot tank and cold tank. From the cold tank the continuously supply to the heat exchanger, and the cold tank, whatever the substance is, will absorb the heat from the substance from the collectors. Okay, there is a heat exchange, and by absorbing heat it is become a hot substance, then it is stored in the hot tank. So this is a thermal storage. Hot tank is a thermal storage. Okay, then that stored is we can use for generating the electricity or any other useful purpose we can use. So this is a one typical heat exchanger. Here the gas is there, and it is completely surrounded by a sealed tube filled with a latent heat storage material. These are the filled tubes. Here there is a latent heat is stored, and that stored energy, and one side it's a gas is in and gas is out, and the stored energy flowing along the coils are tubes, and the tube completely surrounded by this gas, and there is a heat exchange from that container is called as a heat exchanger. It will heat exchange from inside the tube to outside, because outside low temperature, inside high temperature. So it will change the heat from higher to lower. Always heat or temperature is flowing from higher to lower. Okay, so higher to lower. Only exception is refrigeration. In the refrigerator, what happens? Heat is flowing from lower to higher with the help of work. That is different. But here in natural, what happens? In naturally, the heat is flowing from higher to lower. So here gas is having a lower temperature, and inside the coil or tube is higher temperature to heat exchange, and that hotted air gas is again taken for the another section where it can use for any other useful purpose. So this is what the typical arrangements of a latent heat storage system. And here I told some of the organic compounds like substances we can use serves as a heat storage materials due to the desirable property that they have possesses a compare with inorganic compounds. Some of these advantages includes their ability to melt correspondingly their self-nucleating property. They will melt and they will have self-nucleating. Nucleating means rejoining. By adding it, they will split. By rejecting it, they will rejoining. That is what splitting and combining property. They are having self-nucleating, self-splitting properties. They have capability to freeze without supercooling. Means without supercooling, they will freeze. Freeze means change the phase from liquid to solid. Okay, freeze without having super cooling. That is what we want. So they are the compatible properties, and they are conventional materials, and they are easy to construct. So example is paraffin and fatty acids. They are the two candidates organic substances qualify as an heat of fusion materials. And this paraffin processes generally in a high heat fusion and are available for a large temperature ranges, and they're known as a freezing without subcooling. The fatty acids are also known as possesses a reproducible melting and freezing behavior, and these can used as a substance for our latent heat storage systems. Okay, effectively we can use. And also we can use some of the refractory materials also you can use for this process, like MgO, Al2O3, Si2 are also suitable for this high temperature applications where we need a high temperature more than 100 degrees centigrade. Then we can go with this type of materials. Okay. So these are the latent heat storage system. Yes, next class we'll discuss solar pond.